So chapter 11 tells us all about collisions, and we start with impulse. Impulse I is equal to the time integral from 0 to some later time t of f dt, the integral of force. Another way to think about impulse is in terms of momentum. The impulse is some final momentum, p final, minus the initial momentum. It's the change in momentum inside of a system. And when we have objects colliding, the topic of chapter 11, you have changes in momentum. Your book writes this a slightly different way. They use primes, p prime for p final, minus just regular old p for p initial. So be aware of that. So impulse. Conceptually, this equation tells us impulse is just a change in momentum. And you can find this in your book. You can look through your book to see what happens when you invert the equation that you get for impulse. You will find that force is equal to p final minus p initial over change in t, which we should expect because force is a change in momentum over a change in time, which is dp dt. So force is dp dt. So this is equation for impulse is really just the definition of force. It's Newton's second law. Now, how do we actually apply this? So what we're going to do, we're going to try to understand impulse in terms of solving problem number 1 in chapter 11. In this problem, we're given a stuntman with a mass of 77 kilograms, and he belly flops into a shallow pool of water from a height that's equal to 11 meters. When he hits the pool, he comes to rest in 0.05 seconds. We're asked to find the impulse that the water and the bottom of the pool deliver to his body during this time interval. So impulse should get us thinking I is equal to the final momentum minus the initial momentum. That's what impulse is, a change in momentum. I know my final momentum is equal to my mass times my final velocity. And my initial momentum is equal to my mass times my initial velocity. Now I jump off of this diving board and I start falling. So my initial velocity, the velocity I start with, is from rest. So my initial momentum has to be 0. Find my final momentum, I need to know this final velocity. To figure out this final velocity, we need to look at the problem. I have this diving board over this pool of water. I have this stuntman who's going to do a belly flop into this pool. So he's just basically an object in free fall. So we should remember free fall problems from chapter 2 and chapter 3, where we had this height that we fell. His height is actually not just 11 meters, it's going to be negative 11 meters. Because his final position, the place where he ends up with, 0, is lower than where he started with. So final minus initial gives us this negative. I know his initial velocity, v initial, is equal to 0. He starts with 0 velocity. The other factors of interest, the final velocity, that's what I'm looking for. I know his acceleration is equal to negative 9.8 meters per second squared, where I've implicitly assumed, as we usually have, that down is negative. So I have all these variables now. I can use all of these to find my final velocity using the equation vf squared minus v initial squared times 1/2 is equal to a times the change in y, where in this case our change in y is just our height. I can do the algebra here, multiply both sides by 2, to start trying to solve for VF. Get VF by itself. So my 2 and my 1/2 cancel, and I have VF squared minus V initial squared is equal to 2 times A times change in Y. My V initial squared is 0. I take the square root of both sides and find that my final velocity has to be equal to 2 times A times change in Y. You can plug in all your numbers and you will find your final velocity, VF, is equal to 14.7 meters per second. So let's keep that in mind and plug in to find what our impulse is. So continuing onward, we know that the final velocity that this guy belly flops with is 14.7 meters per second. We know the impulse is equal to the final momentum minus the initial momentum. We know momentum is mass times velocity, so the impulse is equal to the mass times the final velocity minus the mass times the initial velocity. The initial velocity was just 0 because we started from rest. And now we can just plug and chug our numbers in. The impulse, I, is equal to the guy's mass, 77 kilograms, times his final velocity, 14.7 meters per second. That's our final momentum minus our initial momentum, which was 0 because of that 0 initial velocity. So our impulse, when you multiply these numbers together, we get 1,130 kilograms times meters per second. So that's the impulse that the water gives to our body. And then the second part, we want to know the time average force. The force is equal to the impulse divided by the change in time. This is something we found at the very beginning of the chapter. This is really just a restatement of Newton's second law. And what I can do now is plug and chug my numbers. Force is equal to the impulse, 1,130 kilograms times meters per second, divided by the total time that I apply this impulse, which in our problem is 0.05 seconds. Divide these two numbers, and you end up with a force of 2.3 times 10 to the 4 newtons. And that's a basic example of impulse. Being a calculus-based course, we have other examples of impulse. We have another definition we could use. We could use an example like number 13 in chapter 11, where I'm given an equation for a force. A force is equal to 3.0 times t plus 0.5 times t squared. I'm asked to find the impulse in this case. I like to think that these problems are a bit easier than the ones where you have to plug and chug numbers in. All you have to do is know a little bit of calculus. You have to know that the impulse is equal to the time integral of force. And we're asked to find this impulse between a time interval from t equals 0 seconds to t equals 3. I can plug in my force equation. Find my impulse is equal to the integral from 0 to 3 seconds of 3.0 t plus 0.5 times t squared, all in the differential dt. So I'm going to integrate this with respect to t. When I do this, I use the power rule and find that the impulse is equal to 3.0 times t squared divided by 2 plus 0.5 times t cubed over 3 at my endpoints of 0 and 3. Now I plug in my numbers, plug in my 0 and my 3 to find I is equal to 3.0 times 3 squared divided by 2 plus 0.5 times 3 cubed divided by 3, and subtract off what turns out to be 0 when you plug in your 0 for t. You multiply this out and get your final answer. The impulse I is equal to 18 kilograms times meters per second. Very nice, very clean problem, all using calculus, just if we know how to do this integral. Now in collisions, there's various different types of collisions we can have, and we can have something called an elastic collision. In this type of collision, kinetic energy is conserved, as is momentum. So in an elastic collision, kinetic energy and momentum are both conserved. This means that the kinetic energy before a collision is equal to the kinetic energy after it. And the momentum before a collision is equal to the momentum after, in the case when our collision is elastic. So what does that look like graphically and equation-wise? Let's say I have a before situation where I have two maybe billiard balls that are traveling towards each other. I have one mass 1, traveling with its initial velocity v1, and it smacks into another mass. We're going to call that mass 2, traveling with a velocity v2. They're going to hit each other, they're going to collide, and afterwards they're going to bounce back. So after they bounce off of each other, I have mass 1. Now maybe it's changed its direction to v1 final, and I have a mass 2 that is now moving in a different direction, v2 final. And to be perfectly clear, we'll make sure we put little initial markings for the initial velocities. So before a collision is equal to after a collision. Momentum before is equal to momentum after, if this is an elastic collision. Momentum before is equal to the mass of the first ball times the initial velocity of the first ball plus the mass of the second ball times the initial velocity of the second ball. And that's going to be equal to the final momentum, which is the mass of the first ball times the final velocity of the first ball plus the mass of the second ball times the final velocity of the second ball. So this is my equation for conserving momentum for two balls that have collided, two masses that have collided with each other. In an elastic collision, the kinetic energy is conserved also. So initial kinetic energy has to be equal to the final kinetic energy. So 1/2 of mass 1 times the initial velocity squared of mass 1 plus 1/2 the mass of the second ball times the final velocity of or initial velocity of the second ball is equal to 1/2 the mass of the first ball times the velocity of the first ball finally plus 1/2 times the mass of the second ball times the final velocity of the second ball squared. So I have conserved both momentum and kinetic energy to get these general equations. And these will work for any elastic collision. So we've discussed elastic collisions, and we'll do an example of those in class. The next type of collision we need to go over are inelastic collisions, and we'll do them specifically in one dimension. In an inelastic collision, K is not conserved. This means that the kinetic energy changes before versus the kinetic energy afterwards. You lose some kinetic energy due to heat or deforming a material or something. So that's the inelastic collision. Kinetic energy is not conserved. You can also have what we call a perfectly inelastic collision. In this type of collision, the kinetic energy is still not conserved, but you also have this condition where particles stick together afterwards. So let's take a look at an example of a perfectly inelastic collision. So this is going to be problem number 40 in chapter 11. In this problem we have a 25 kilogram boy. So we have this boy, He has a mass of 25 kilograms. And he's on a 10-kilogram sled that's coasting at 3 meters per second on level ice toward his 30-kilogram sister. So let's write down everything we learned in that first sentence. The mass of the boy is 25 kilograms. We have the mass of this sled. The mass of this sled is equal to 10 kilograms. And they're traveling along, they're coasting along at some initial velocity. The velocity of the boy plus the sled is equal to 3 meters per second squared. And then the little girl is 30 kilograms. Mass of the little girl, mass of the sister is equal to 30 kilograms. Okay, so we've written down everything we learned in that first sentence. Second sentence tells us the girl jumps vertically and lands on her brother's back. And we're asked to find the final speed of the siblings in the sled, and we can neglect friction. So what happens is we have this boy on this sled. So the initial picture we can draw, the before situation, is a boy on a sled, and he's moving forward, traveling towards his sister. The boy and the sled are both traveling at some initial velocity. And initially, we can assume that the initial velocity of the girl is equal to 0. She's just standing there. Then the after situation, we have this boy on this sled, he's still traveling forward. And we have this girl that jumps onto his back. So we're going to somehow depict that the girl jumps onto his back, and they're both going to take off and continue in the same direction they were going. And they're going to continue at some final velocity. Conceptually, we can probably make sense that the final velocity is going to be less than the initial velocity. And we can solve this using momentum, using conservation of momentum and the fact that this is a perfectly inelastic collision. We're not told anything about the kinetic energy. We can't assume kinetic energy is the same before and after. All we know is that the momentum is always conserved. Momentum initial is equal to momentum final. So we know this is an inelastic collision. How do we know it's perfectly inelastic? Well, we can see that right here. In the situation before, we have two separate masses. We have the mass of the boy and the mass of the girl. In the after situation, the girl jumps onto the boy's back. So it's like they've combined masses. The masses have combined in the after situation. So the masses are sticking together. So our initial momentum is going to be the mass of the boy plus the mass of the sled times their combined velocity. And that makes sense. Initially, we have this boy and this sled. We combine their masses, and they're moving at a combined 3 meters per second. That's going to be equal to the final situation I have, where I have the mass of the boy. He's still traveling along. He's still on the sled. But now we also have this additional mass, the mass of the girl. And she is traveling together with the boy and the sled at some final velocity. So just to recap and to plug in some numbers, we have the initial momentum is equal to the final momentum. Initially, the momentum in the system is the total mass of the system, mass of the boy plus the mass of the sled times the initial velocity. Then the final situation, we still have the mass of the boy and the mass of the sled, and then we're adding on the mass of the girl. So we have a slightly larger mass, and then that's going to be multiplied by our final velocity to get our final momentum. We can solve this for the final velocity. The final velocity is equal to the mass of the boy plus the mass of the sled times the initial velocity, which is basically just the initial momentum, divided by the final mass, the mass of the boy plus the mass of the sled plus the mass of the girl. And if we plug in all these numbers, we can find V final is equal to 25 kilograms, the boy's mass, plus 10 kilograms, the sled's mass, times the initial velocity of 3 meters per second, all divided by 25 kilograms, the boy's mass, plus again the 10 kilograms of the sled, plus the mass of the sister, 30 kilograms. So if you plug in all your numbers, we find the final velocity is equal to 1.6 meters per second. And we've just done a perfectly inelastic collision, where before we have some mass that's traveling along, and then afterwards we have the mass sticks together, masses that stick together after your collision. And as a final note, the final section in the book for this chapter discusses what to do with 2 and 3D collisions. And in this situation, you do what we've always been doing. Collisions in multiple directions, still conserved. It doesn't matter that you're moving in the X and the Y directions, the collisions are still conserved. And much like projectiles, and much like forces, they're conserved in the individual directions. So we have to separate collisions in multiple dimensions into their respective X, Y, and Z components. And we'll do a problem in class, an example of that, to see what multiple directional collisions look like.